Welcome back to our course on blockchain and its applications. So, in the last class, we have learned about this collective signing mechanism. So, today we are going to see that how we can effectively utilize collective signing to solve some of the problems which are associated with Bitcoin NG, followed by how we can improve the scalability of the blockchain consensus further with the help of combining collective signing along with the proof of work based consensus mechanism. So, today we are broadly covering this concept of ByzCoin, which is a kind of blockchain consensus protocol that combines proof of work with PBFT. So, we are going to see that how we can combine proof of work along with PBFT to solve this particular problem of consensus scalability. And then we are going to look into that how far we can achieve in supporting the blockchain consensus in terms of scalability with the help of such kind of architecture. So, these are the keywords for today's talk, today's lecture. ByzCoin, we are going to talk about this specific mechanism. We are going to learn about something called an open consensus group. We are going to see that what is meant by open consensus group and how we can achieve to develop an open consensus group. And finally, we are going to learn something interesting which is called the blockchain performance triangle, and we are going to learn about the different kind of trade off that we have while designing a scalable blockchain architecture. Now, to start with, let us revisit the requirements of blockchain consensus that we mentioned earlier. We are just going to touch upon each of the requirements briefly. So, our first requirement was to make the protocol Byzantine fault tolerance, because we assume that the participants in the blockchain network, they can be faulty in terms of malicious behavior. So, they can behave maliciously, and as a consequence we need to design an architecture, we need to design a protocol which is Byzantine faulty. We need to ensure that the system should work even in the presence of malicious users while operating across multiple administrative domain. The second requirement is to provide strong consistency guarantee across replicas. So, we need to ensure that the different replicas which are available with individual peers of my blockchain network, every peer or every node have the same copy of the replica with them at the same instance of time. Then we need to ensure that my consensus algorithm should scale well to increasing workloads in terms of transaction processed per unit time or transaction per second. So, I need to ensure that I should be able to support maximum number of transactions that can be processed per second or per unit time, and that we typically call as the transaction throughput. So, I need to ensure scalability in terms of transaction throughput. And the final requirement is that my protocol should scale well to increasing network size. So, that way the protocol should also work good when my network is large. So, earlier we have seen that this proof of work and PBFT, they basically have a trade off between the last two requirements. So, whereas PBFT, it scales well in terms of increasing workload, it does not work good with a large network size because it is based on message passing. On the other hand, the proof of work type of algorithm, it can really support large number of participants, large number of peers in the network, but on the other hand it does not scale well in terms of transaction throughput, the amount of transaction that can be processed per unit time. So, that way I have a trade off between PBFT and proof of work, and we need to design a protocol that can balance these two trade off. So, with that particular objective, we have seen this idea of Bitcoin NG, where Bitcoin NG separates out the transaction serialization from leader election. So, it uses proof of work to elect a leader. So, that leader basically proposes a key block followed by a number of micro blocks. So, this micro blocks helps adding up additional transactions in the blocks. So, that is good. With the help of micro block, as we have seen that we can increase the transaction throughput significantly compared to the standard Bitcoin proof of work consensus mechanism. But there is a inherent problem in this architecture. So, what is the problem? The problem is that a faulty key block is verified only after the end of the round. So, that means, if a miner becomes faulty and it is being elected as a leader and it starts adding up a faulty key block in the system, then that leader is replaced only in the next round. So, when you are going to have next round of proof of work and in that next round of proof of work you are going to elect a new leader, then the old leader becomes invalidated, and by that time the old leader might have added multiple other micro blocks, and because the old leader has added multiple other micro blocks, so basically the key block along with all the micro blocks that become invalidated. So, that way it is certainly a kind of overhead for the system, and that way what might indeed happen, that a faulty miner it can introduce several correct micro block following a faulty micro block. So, what it can do, that it can add up a key block followed by a faulty micro block followed by several other correct micro block. Well, so in my entire end-to-end architecture, if a miner add up one faulty micro block within its set of key block and the micro blocks that it is going to add, out of them if only one micro block is faulty, then I need to discard the entire chain, right. That means, starting from the key block to all other micro blocks. This is the kind of overhead as I mentioned, and if I have a fork, that alleviates the problem further. So, I have a micro block fork and maybe that micro block forky micro block is faulty. So, if the fork micro block is faulty, then actually the majority of the participants, they are not going to validate that, maybe one or two of them are going to identify that, well, that micro block is faulty, but in the system I need to ensure that the miner who has added up that faulty micro block, even if it is a part of the fork network, but still I need to ensure that all the existing micro blocks and the key blocks corresponds to that miner in that round, that need to be removed. Well, so this kind of overhead gets introduced, and what a malicious participant can do, a malicious participant can create a denial of service kind of environment by introducing such kind of faulty micro block in the system. So, it participates as a legitimate user, when it participates as a legitimate user, it gets selected, and once it gets selected, then it injects a correct key block. People think of that, well, this is a good participant, and then it adds up one or two correct micro block followed by one suddenly a kind of faulty micro block it injects in the system. And because of that reason, the other nodes in the network, they have to remove all these key block and the micro blocks in that round, and then again start with the next round. So, that kind of overhead may get associated to it in the system, and that can slow down the entire process. So, this is a typical issue because the micro blocks are not getting further validated. So, the key blocks are getting validated, the key blocks are elected by a mining procedure, but once I am becoming a leader, I am getting access to a generate a key block, then I can have the liberty to add up further micro blocks in the system. So, those micro blocks are not explicitly getting validated before adding them up in the network. So, that is the kind of source of the problem that we have with Bitcoin NG. Now, what can be a possible solution for this problem? Now, to solve this problem, what we can do, that we can solve this problem with the help of a set of PBFT verifiers. So, what are those PBFT verifiers? So, these are some of the nodes that verifies or that collectively verifies that the microblocks which is going to get added in the system, that microblock is correct. Well, and once this PBFT verifiers verify that, well, this microblock is correct, then only I will be adding that microblock in the system. And why I am using PBFT verifier? So, PBFT means you already know practical Byzantine fault tolerant. So, I am just adding up certain nodes in the system which will verify that this microblock has not been generated by a Byzantine node, and while doing that verification, it might also happen the node which is verifying that node itself is Byzantine, or that node itself is malicious, because the faulty node might have colluded other nodes in the network. So, that kind of scenario might happen, and because that kind of scenario might happen in the system, I need to prevent it from having Byzantine attacks. So, I can use a set of PBFT verifiers to verify every microblock and the key block before they are getting added in the system. And here I can utilize the idea of this Byzantine agreement protocol. As we know that Byzantine agreement protocol within a small consensus group, it works really fast. So, that way I can have a set of PBFT verifiers which can quickly check that well this particular microblock is good, and once they are authorizing that this particular microblock is good, then that microblock gets added in the system. So, that idea works well in such a context. So, that way I can avoid introducing faulty microblock in the system by a elected leader or a elected miner. But if I just try to look into the scalability issue of PBFT. So, what is my problem? Well, so whenever we are going to utilize PBFT, what we have seen that PBFT requires a static consensus group, well, because it is based on message passing. So, what we have seen earlier. So, because PBFT is based on message passing, so what might happen that I need a kind of static set of nodes which are going to work as my verifier. But with a static set of nodes, my problem is that if those set of nodes are getting colluded, then my entire system might violate safety. Well, so I do not want to have a kind of static consensus group, because I am relying on a subset of the users, a small set from that entire network who are going to quickly validate every microblock. So that way, from that context, static consensus group is not suitable for this purpose. Well, and also if I just try to look into this complexity of PBFT in terms of node, if I try to look into the scalability aspect of PBFT, what we see that scalability is a problem for PBFT in terms of number of nodes. So, I have O of n square communication complexity when I have n number of nodes in the system, and I have O of n verification complexity. Well, and also I do not have any third party verification proof. Well, so typically PBFT uses message authentication code, and for that you need to share the keys among the miners. Well, now if you want to share the keys among the miners, you actually need to know who are the other miners in the system, and finding it out is very difficult. Well, because we are talking about a kind of open network where we are going to run our protocol. Now, in an open network, if I try to run our protocol and if I claim that I need a kind of message passing based algorithm, obviously I cannot solve that problem here. Another issue is the Sybil attack. If I just think of a PBFT set of PBFT verifiers which form a static or a fixed consensus group. So, what might happen that a malicious node can create multiple pseudonyms or pseudo-anonymous identities to subvert that 3f+1 requirement of PBFT. And all these problems are coming because I am going to select a subset of all the users who are going to work as a PBFT verifier. Well, so you can just think of that, say this is my set of users who are there. So, this is my say I am naming the protocol as ByzCoin. So, this is the set of ByzCoin users, and out of those ByzCoin users I am going to select a subset of them. Maybe this set of nodes they work as the PBFT verifiers. Okay. And because a subset of nodes are going to work as a PBFT verifier, so that is why the problem is that whenever I am using this subset, if this subset gets colluded and majority of the users within that subset is malicious, then this entire protocol violates safety. Well, because they are someone who is going to validate whether that microblock is faulty or not. So, this is the particular problem that we face if I am going to work with PBFT, and these are the particular issues that I have with PBFT. And then if I just try to open the consensus group, well, so that is the core idea in this protocol, that you use PBFT, but you use PBFT within an open consensus group. So here you might get surprised that how I can open up the consensus group, because by default PBFT is something that needs message passing. That way the participants in the PBFT network, they need to transfer the message with each other. So how can I do it in an open network? Well, so what we can do, that we can use proof of work based system to give a proof of membership of a miner as a part of the trustee. So what are the trustee? So the trustees are the members of the consensus group. Or the set of verifiers that I were talking about earlier. Okay. So what I am going to do, that I am going to select this set of verifiers or going to select that consensus group with the help of proof of work. Well, and to maintain a kind of balance of power within the BFT consensus group, what we are going to do, we are going to use a fixed size sliding window. Now, each time a miner finds a new block, it receives a consensus group share. We are going to discuss about how this is being done with the help of an example, and the share proves the miner's membership in the trustee group. Okay. So, let us try to see with an example that how it works. So, this is the particular paper that we are going to discuss now, which proposes this idea of ByzCoin. The title of the paper is Enhancing Bitcoin Security and Performance with Strong Consistency via Collective Signing. It got published in 25th Usenix Security Symposium. So, this particular paper, it proposed the idea of combining collective signing along with proof of work to design this idea where we are going to select a subset of the miners who form a trustee group or a witness works like a witness cosigners that verify every microblock which are going to get added in the system. Well, so this is the idea to merge BFT consensus along with proof of work in ByzCoin. So, you validate each microblock by a set of witness cosigners. Well, so who are these witness cosigners? And these witness cosigners are the members of the trustee group that we are talking about. Well, and how it works? So, I have the structure for the Bitcoin NG. So, in Bitcoin NG we had this key block and other microblocks. Well, now here my requirement is that before adding a microblock in the system, I would get it verified with a set of verifiers. Well, a set of verifiers. Now, this set of verifiers are going to verify that this microblock is correct. If they verify that this microblock is correct, they are going to put up a collective signature on this microblock saying that all of us are certifying, or at least the majority of us certifying, that this microblock is a valid microblock. Now, here you see that the moment I am saying that I am going to use approach where multiple witness or the members of the trustee group, they are collectively verify and collectively sign a microblock saying that this microblock is a valid microblock, I can use the collective signing approach that we have discussed in the last lecture. So, in the collective signing approach, what we have seen that what we can do, that we can use this BLS encryption or such kind of collective signing mechanism to collectively sign a particular message. So, here this message is basically this microblock that is being generated. So, these validators, they can validate whether this microblock is valid, if this microblock is valid, then they collectively sign it, certifying that hey, this microblock is valid, that can be added to the blockchain. And what we have seen earlier, that my 2 rounds of COSI is equivalent to the 3 rounds of PBFT. So, that means on this particular microblock, using this microblock as my message M, if I run 2 rounds of COSI based on the protocol that we discussed in the last lecture, then that will emulate the 3 rounds of the PBFT. That means the prepare and commit phases of PBFT. So, that way I can use this set of verifiers to validate the microblock. But the question comes that how I am going to find out that who are going to be part of this this verification group, or the trustee group, or the witness cosigner group, whatever name you give it. So, for that what we do, we validate each microblock by a set of witness cosigners, but as I mentioned that our question is that how do we select these witness cosigners and create this trustee group or a consensus group. So, what we do, that we select them from the miners. Well, so we have these key blocks. So, these individual blocks are the key blocks, and we find out that which miner has mined how many blocks. So, I can take a kind of window. Well, so this dotted line actually signifies the window. So, maybe I am going to look into last 7 key blocks, and in that last 7 key blocks I am going to find out that who are the miners that have generated the key blocks, and those miners become part of the trustee group, okay, or the members of that witness committee. So, here I can see that this YOLO miner, it has generated this two key blocks. So, its share is 2 by 7. Similarly, this red miner, it has generated 2 key blocks. So, its share is 2 by 7, and this blue miner, it has generated 3 key blocks. So, its share is 3 by 7. Well, now based on that share you create this tree, that is the COSI tree that we have seen earlier, and in that COSI tree these miners, existing miners who are there, they will form that COSI tree, and then they will run that collective signing mechanism to sign the microblocks which are going to generate it after this particular key block. Okay. So, after this particular key block I will have multiple microblocks. So, these microblocks will be validated by this set of miners who will form that consensus group. Now, here you see that as I make progress, if I just think about my window size is equal to 7, that means this window is continuously moving, and that way the tree structure is getting changed, the participants in the PBFT consensus group, that is getting changed. So, I am not bound to a fixed PBFT consensus group, rather I am continuously keeping on changing the PBFT consensus group. But the interesting fact here is that I am taking help from the miners who have already mined the block, and that information is already public, because you can see that who is the miner who has mined this block, and by getting that information you can actually share the messages among those miners to get the things validated. Well, so the information, say for example, here by looking into the blocks in the window you can find out this red miner, blue miner, and the yellow miner, and these 3 miners can share the message among themselves to run the COSI protocol, the collective signing protocol. So, this is the core idea behind ByzCoin, where we are combining proof of work along with PBFT, and here we see that this idea of combining proof of work with PBFT, it actually improves the efficiency of BFT consensus with the help of COSI. Well, so we improve O of n communication complexity, because we are using tree based multicast protocol. So, we can use O of log n right now. So, earlier we had O of n n square communication complexity. So, this should be O of n square. Now, to improve in terms of the verification complexity, we use Schnorr multisignature. Now, the idea of the Schnorr multisignature, as we discussed in the context of COSI, that you can generate that collective public key, and once you are generating that collective public key, so if the public key for individual signers is g to the power xi, then my collective public key is product of g to the power xi. So, once I have this collective public key, I can use this collective public key to directly verify it. So, that way my verification complexity would be O of 1. Well, so that way I can see that well for the communication complexity compared to the standard PBFT, I can reduce it from O of n square to O of log n. Well, and in terms of the verification complexity, earlier it was O of n. Now, with the help of this Schnorr multisignature or the BLS encryption mechanism, whatever you use, I can make it to O of 1. Now, this as we learnt in the last class that this multisignatures plus communication tree that actually constitute this collective signing mechanism. Well, and we can efficiently use collective signing mechanism to collectively sign that microblocks, so that it validates the authenticity of the generated information in the corresponding microblock. Now, if I just try to look into ByzCoin performance with different examples, different use cases. So, here you can see that with 32 MB block size, I can reach a performance which is close to PayPal. Well, although I have a gap from Visa, we are not been able to reach up to the transaction throughput which is typically supported by Visa, but the transaction throughput which is typically supported by PayPal, that can be crossed, that can be reached with the help of a 8 MB block size. And remember in Bitcoin we had that 8 MB block size. Now, with this 8 MB block size I can reach up to this, and with 32 MB block size or 16 MB block size we can cross PayPal. Well, but here we see that we still have this gap. Well, so that is something we need to think of. We need to think of further, or we need to look into. So, what we have seen that with the help of ByzCoin I have been able to improve the performance. Well, I can reach the scalability, transaction scalability close to PayPal, and the node scalability it is equivalent to Bitcoin, because we are just using the Bitcoin miners to create that consensus group, and the members of the consensus group sign the message. But that way I can significantly improve the scalability, but still I have certain gaps. So, the question comes that how we can fill up this gap. So, if I just try to summarize that we have learnt in ByzCoin, that this ByzCoin solves the problem of introducing a faulty microblock in Bitcoin NG, which can severely affect the performance of Bitcoin NG. It combines proof of work with PBFT with the help of COSI. So, it opened the consensus group with the help of COSI, and selecting the members of the consensus group or the trustee group or the member of the witness cosigners, whatever term you use, all signifies to that consensus group. So, by considering the mining share of individual miners within a last window size. And the question that remains that how can we achieve internet scale scalability? Well, both in terms of performance as well as in network size. Well, as we have seen that still we have certain gaps from the transaction throughput which is typically supported by PayPal. Now, in that context, if I just try to recap Bitcoin and try to see that what are the advantages that we had in Bitcoin proof of work and what are the disadvantages that we had, and try to see that how we can make the balance, that will possibly give us some idea that how I can fill up that small gap or that we have seen in the ByzCoin performance. Now, in Bitcoin the key idea is that we achieve consensus through proof of work. So, that means it is a complete open consensus. In Bitcoin the communication protocol that is being used is the gossip protocol. So, the nodes gossip with each other to share the blocks, and the key assumption is there is that the honest majority of the mining computation power. So, the miners who are there, they are honest and they have the kind of majority of the consensus power. But if I just try to see the limitations of Bitcoin, first of all, it has significant resource wastage, it had high computational power, it takes a lot of electricity cost because the computation is much more challenging. Then it can have this concentration of power. Typically 5 mining pool they control the entire system, and when around 5 mining pools they control the entire system, there can be possible vulnerabilities. So, you can easily track who are the miners, and you can just collude those miners. So, as I mentioned that the entire system is concentrated to a few mining pools. Well, so you can actually see it from the ByzCoin block explorer. So, if you just try to look into the ByzCoin block explorer, so these are the recent blocks that have been mined. Here if you try to see that who are the last miners. So, here you can see that well, this was the AND pool, then F2 pool, /pool, again /pool. Okay. So, the unknown cases where the miners are not known. So, we can just ignore it, try to look into the mining pool that has mined the ByzCoin blocks. So, here I see AND pool, F2 pool, /pool. Then if I just go down, so here you can see again AND pool, again /pool, again F2 pool, /pool via BTC, AND pool, /pool. Okay. So, here you can see that some miners are continuously getting repeated. Again if I go down, then I have this via BTC, AND pool, F2 pool via BTC. Okay. So, the same set of miners are continuously getting repeated. Well, so that we see from here. Now, if that is the case, that is my problem, then the challenge that we have is that the entire mining power is getting concentrated. Well, and when this mining power is getting concentrated and few miners they are taking hold of the entire system, then the system becomes vulnerable. Well, and other problems of ByzCoin is that the scalability issues. Well, so the number of users, it is not clear that how many number of users it support, whether it is 1 million, 10 million, 100 million, because we do not have any mathematical bound, but we see that it has high latency. Well, so around 10 minutes to mine each block on average. Well, and with the help of fork there might be ambiguity, and fork actually alleviates all this problem. Well, it does not help the system to reach to the consensus finality as we discussed earlier. Now, this is the interesting stuff, that if I just try to look into the aspect of blockchain consensus, this we call as the blockchain performance triangle. I have 3 parameters: scalability, security and decentralization, and actually you see that these 3 are actually having a trade off with each other. Well, we cannot or at least with the protocols that we have discussed till now up to ByzCoin, they are not been able to satisfy all 3 together. If I am going to have complete decentralization, I have to compromise with security. If I focus on scalability, then I have to compromise with decentralization. Well, if I focus on say decentralization and the scalability, complete scalability, I might have to compromise with security. So, this kind of trade offs are there. Well, now with this trade off, the question that remains that is it ever possible to achieve all these 3 requirements simultaneously? That means scalability, decentralization and security. Well, so that we are going to discuss in next lecture in details. So, thank you all for attending this lecture. See you all in the next lecture. Thank you.